Let's wait for 5 minutes and then we'll start. Okay, let me start the session now. So welcome to the week 4 of this live interactive session. Uh, the course is NOC24 EE-28 Signals and Systems. And I'm Yawar, a PhD student at IIT Kanpur. The instructors of the course are Professor Hitesh Remali and Professor Kushal Kesha from IIT Mandi and IISER Bhopal respectively. Now, the prerequisites of the course include the last week's lectures that covered the following topics, namely the Fourier transform properties, the Fourier transform of noise and types of noise. I'm sure you would all have gone through those videos and you must have attempted the assignment 4 before watching this session. Okay, we went through these definitions in the last interactive session as well. I had a small typo here and I've corrected that. You can refer to the updated slides in the shared Google Doc. Now let's go through these properties of Fourier transform before attempting the questions. So linearity, we have already discussed that this Fourier transform is linear and given two signals x1 of t and x2 of t having Fourier transform x1 of omega and x2 of omega respectively, then the Fourier transform operation will be linear, right? And this can be readily uh, observed from this linearity property of integrals. The second property is the time shift property, and given a signal x of t and its Fourier transform pair x of omega, the Fourier transform of this time shifted signal x of t minus t naught is simply e to the power minus j omega t naught x of omega. Okay, and then we have this duality property, uh, that is this x of t x of omega. Given we have this, the following thing holds good. That, I mean, notice we are changing the functions, right? The function that was in the frequency domain, I'm using that in the time domain, and the one that was in the time domain, I'm using that in the frequency domain in this dual property. And then we have the frequency shift. It's actually a dual of this time shift property. Uh, if we have this shift in frequency in the frequency domain, suppose if the shift is by this omega naught, then the time domain signal x of t is simply multiplied by this e to the power j omega naught t. Okay, and then we have some more properties of Fourier transform. Let's go through them. The time scaling property is one of them, which states that given the Fourier transform pairs x of t x of omega, x of at, the time scaled version of this x of t, right? That is given by 1 by modulus of omega a x of omega by a. I will not be discussing the proof because I'm sure you would already have gone through the proofs, but in case you have any doubt, you can ask in this session and I'll address that. Then we have this differentiation in time domain. Okay, given the signals x of t, the time signal x of t, and its Fourier transform x of omega, if we take a time derivative of this x of t in the time domain, the frequency in the frequency domain, what happens is that it gets multiplied by j omega, right? So if x of t had Fourier transform x of omega, I take the time derivative of this, the frequency domain signal gets multiplied by this j omega. And then we can generalize this differentiation in time domain property by following. That is, this nth order time derivative of this x of t is j omega raised to the power n x of omega. One can easily see how this generalization comes about, right? And then we have the integration property, uh, which states that if x of t is a time domain signal, then this integral minus infinity to t x of tau d tau, the Fourier transform of this particular signal is given by this, right? X of omega by j omega plus pi x of 0 del of omega. Convolution is the next property, which states that, uh, I mean, if we convolve the signals in the time domain, I'm sure you are aware of this convolution operation. If not, we'll discuss the sample problems and it will be clear. So the time convolution of the signals, I would say the convolution of the signals in the time domain, the Fourier transform of that particular thing is as if we multiply the frequency domain signals, right? X of t had Fourier transform x of omega. Y of t had Fourier transform y of omega. I took the convolution in the time domain and I'm multiplying the individual Fourier transforms. I'm literally multiplying them, right, in frequency domain. So that's the convolution property. After that, we have this multiplication property, which essentially is a dual of this convolution, right? What if we convolve the signals in the frequency domain? Then the signals x of t and y of t get multiplied, right? And notice there is a factor 1 over 2 pi here. Then we have this complex conjugation, that is given the Fourier transform pairs x of t and x of omega, we have following x convolution, sorry, I mean, this is conjugate, right? This is conjugate of x of t. Conjugate of x of t, if I'm taking conjugation in the time domain, what happens in frequency? The conjugation with time reversal, right? If you have not gone through proofs, I would suggest you to try them out. They are pretty straightforward. Then there is differentiation in frequency domain. Okay, we had this differentiation in time domain, right? This is just dual of that. Here, what was happening? I was taking derivative of the signal in time domain and j omega was multiplied in the frequency domain. What happens when I take derivative of the signal in frequency domain? Minus jt gets multiplied in the time domain, right? And this is the generalized result of the same. Now with that, we can start with the first sample question of today's session. That is, if the Fourier transform of x of t is x of j omega, I mean, whether I write x of j omega or x of omega is one and the same thing, right? I'm just writing this x of j omega as x of omega for simplicity. Okay. Now, what is the Fourier transform of this? This is second order derivative of time of this x of t. Let me wait for 1 minute if someone can answer this in the chat, and then I'll start doing it myself. Please try this. I hope I'm audible. I hope so. Okay, let me now try this myself. So this actually is nothing but a special case of this property, right? Where this n is 2, right? I'll directly use that. Use a separate page though. Okay, so for n is equals to 2, we'll have d2 d square by dd2 this x of t. That would be j omega square x of omega, and j square is -1, so it would be minus omega square x of omega. I mean, which option is correct then? This one, right? Why? Because this is same as this. For simplicity, I'm just using x of omega instead of x of j omega. Okay, so option B was correct. If you have any doubt, just let me know. Otherwise, we can move on to the next question. The Fourier transform of sine of t u of t. I'll wait a minute. You guys may attempt it and let me know the answer in the chat. Which option is correct? You might need these results, right? U of t. We saw this in the previous session that u of t, the Fourier transform of u of t is pi del of omega plus 1 by j omega, right? And you also know that sine of t is e to the power jt minus e to the power minus jt multiplied by 2j, right? You know these two results. You may use them and see if you can solve this one. Okay, so this sine of t u of t, you may write this as 1 over 2j e to the power jt ut minus e to the power minus jt u of t, right? I just used this one. Now, computing Fourier transform of this sine of t u of t, same as if I compute Fourier transform of this one. Okay, so I'll do that. Let me compute the Fourier transform of this one. T u of t minus e to the power minus jt u of t, right? Fourier transform is a linear operation, so mean I can compute the individual Fourier transform of this and this. What is the Fourier transform of this? You are multiplying e to the power jt in time domain. So this, I know the Fourier transform of u of t, right? And I'm multiplying e to the power jt to that in time domain. Which property should I use? Frequency shift, right? E to the power jt, consider omega naught as 1, then e to the power jt is getting multiplied in time domain, right? That is essentially a frequency shift in the frequency domain. So let me shift this signal by 1. Which signal? This signal, right? The Fourier transform of u of t. So this is these red arrows indicate the Fourier transform of the e to the power jt u of t, and likewise I compute the Fourier transform of e to the power minus jt u of t. Now we are multiplying this by e to the power minus jt, right? So omega naught is minus 1, right? If omega naught is minus 1, omega minus omega naught would be omega plus 1. So, right? So it's pi del of omega plus 1, 1 over j omega plus 1, right? So now I'll just club these two, right? The Fourier transform is the subtraction of these two Fourier transforms. So, okay. Sine of t, u of t, I had to compute the Fourier transform of this signal. What is that? That is 1 over 2j, 1 over 2j. I'm writing this one now, pi del of omega minus 1. Okay, why minus sign? Because there is a minus sign, right? That's why. So now this is plus 1 over j omega minus 1. Using color coding, maybe that would make it more clear. Then we'll have this negative sign, right? Is this clear? I hope it was clear. I even used colors to denote the individual Fourier transforms. So let me repeat what I did. Sine of t u of t, I had to compute the Fourier transform of this, right? I can write this sine of t u of t in this form. That is pretty straightforward. Then what I did was I computed the individual Fourier transform e to the power jtu of t and the Fourier transform of e to the power minus jtu of t, right? I notice that I know the Fourier transform of u of t, and essentially you are multiplying e to the power jt in the time domain. That is nothing but a frequency shift in frequency domain, right? So I knew what was the result of this u of t. That was pi del of omega plus 1 by j omega. I shifted that by 1 unit. Why? Because omega naught was 1, right? That's how this result came. And similarly, I came to this result. And why? Because omega naught was minus 1, right? This is e to the power j omega naught t. The only way it would be e to the power minus jt is when this omega naught would be minus 1. So if omega naught is minus 1, then omega minus omega naught. What is that omega minus omega naught? That is omega plus 1, right? That's why I replaced omega by omega plus 1 throughout this result, right? So then the Fourier transform of sine of t u of t would be 1 of 2j. The Fourier transform of this, that is this one. Why is it not working? This one, see this and this, minus this. So there would be a minus sign with pi of del of omega plus 1 and a minus sign with 1 by j omega plus 1. So that is why this and this. So which option is correct? The correct answer is option B, right? That is where we, I mean, that's what we got. Okay, now the third question. I hope it was clear. If not, you can ask questions. Now the third question is the transfer function in frequency domain of the equation 1 is you have been given a differential equation and you need to compute the transfer function, right? I hope this would have been taught in the week's lecture. I mean, the last week's lectures would have covered this. Given a differential equation, you can compute the transfer function by just using a Fourier transform. Okay, let me solve this one. So this one is question 3. And this is our equation. Right, this is your given equation. And what we'll do is we'll use Fourier transform on both the sides, right? So notice this is d2y by dt square, taking a second order derivative of y of t, right? Suppose this y of t has a Fourier transform y of omega. What should be the Fourier transform of d2y by dt square? We actually did that in the question 1 itself, right? The Fourier transform of this is minus omega square x of omega, right? X of j omega or x of omega, just a notation game. Okay, so using Fourier transform, for simplicity, what I'll do is I'll use this property, right? J omega raised power n, right? I mean, if the order was 3, I would have taken j omega raised to power 3, right? And similarly so on. J omega square y of omega plus 4 j omega raised power 1 plus y of omega plus 3 y of omega, right? Okay, so now this is equals to d by dt of x of t, and that is j omega raised power 1 x of omega plus 2 times x of omega. Okay, now I'll take y of omega common on the left hand side and x of omega common on the right hand side. That gives me y of omega minus omega square plus 4 j omega plus 3. Now that is x of omega common, that is j omega plus 2, right? Now what is y of omega by x of omega? That is j omega plus 2 whole divided by minus omega square plus 4 j omega plus 3. Okay, this is the result. Now, which option is correct? The correct answer is option A, right? Option A is the correct answer. Okay, the question number 4 is what is x of t, y of t in the frequency domain, right? This dot is multiplication operation, right? So this is given a signal x of t, which has a Fourier transform x of j omega or x of omega, whatever. Y of t, a signal that has a Fourier transform y of omega or y of j omega. What is the Fourier transform of the product of the two signals? If you remember, I had actually kept this result as a property, right? Put this one. The product of x of t, y of t is given by this one, 1 by 2 pi x of omega, convolution y of omega. But I'll do one thing. I'll show a proof for this, and maybe you can go on the similar lines and try to prove the dual of this. What is the dual of this? If you have this, you know, x of t convolution y of t, you'll prove this one, right? This would be a homework for you. You will prove this one. I would prove this question, right? A product in time domain. That's what I would prove. So let's start. We already know, right? The answer is 1 by 2 pi. The answer is 1 by 2 pi x of omega y of j omega. But we'll still go through this proof. So this is question number 4. And I need to prove the following. See, the statement that I made was that x of t, y of t, the Fourier transform of this is given by 1 by 2 pi x of omega. Throughout this session and throughout all other sessions, I'll be using x of omega instead of x of j omega, right? Just for notation simplicity. X of omega convolution y of j omega, sorry, y of omega. Right? This is what I need to prove. So in other words, I need to prove that the inverse Fourier transform of this one. Let me just copy paste it. That would save time. Inverse Fourier transform of this signal the inverse Fourier transform of this signal is x of t, y of t, right? Product of these two signals. Now, we'll suppose that this signal 1 over 2 pi x of omega y of omega, let this be z of omega. Okay, so by definition, what is the inverse Fourier transform of this z of omega? The inverse Fourier transform of z of omega would be 1 over 2 pi minus infinity to infinity z of omega e to the power j omega t dt. I mean d omega. Right, that is what the inverse Fourier transform of z of omega is by definition. So now let me use another page. One over 2 pi minus infinity to infinity z of omega is this, right? 1 by 2 pi. I'll use that. 1 over 2 pi x of omega convolution y of omega. then is e to the power j omega t and d omega. Is that clear? Then what I would do is this operation, you all know that this is a convolution operation, right? And let me even write that this x of omega convolution y of omega, that by definition is minus infinity to infinity this x of tau, right? And y of omega minus tau d tau. That's what this quantity is by definition. Okay, so let me use that. I have two 1 over 2 pi factors. Okay, so I have two 1 over 2 pi factors, right? I'll club them. So inverse Fourier transform of z of omega, that would be 1 over 2 pi squared. I have these two integrals now. This is one integral and this is other integral. Right? And then I have these x of tau, y of omega minus tau, d tau, and this factor e to the power j omega t, d omega. Okay, I guess everything should be okay up to this point. Then this is 1 over 2 pi squared minus infinity to infinity. So see, I can take this out, right? Since this does not depend upon omega, I can take this out. I can take this out, right? And I'll multiply this by e to the power j tau t and e to the power minus j tau t, right? So let me first write that x of tau e to the power j tau t. In fact, I should use something different. I guess this one e to the power j tau t, right? D tau minus infinity to infinity y of omega minus tau, and I have this e to the power minus j tau t, right? That is what I was trying to say. I'm adding this and e to the power minus j t. The product of these two is 1, right? I can do that. So then I'm left with this part e to the power j omega t d omega. Right now, uh, This, we can club this into a common exponential. This is e to the power j omega minus tau t, right? And what I'll do is I'll then put, let me do one thing. See, this is equal to e to the power j omega minus tau t. I'll replace this by this. Okay, let me do that. Done. Now I'll use following substitution. I'll use this one, omega minus tau. I'll put that as alpha. What would that give me? That would give me d omega as d alpha, right? Because this integral, for this integral, tau is essentially a constant, right? Omega is the variable of integration. So now when omega tends to minus infinity and omega tends to plus infinity, right? You need to tell me what will happen to alpha, right? Because that is what I'm trying to convert this integral into. What value should alpha take? Right, pretty straightforward. Alpha would also tend to minus infinity and alpha would also tend to plus infinity when omega would be minus infinity and plus infinity respectively. Okay, so this particular quantity is alpha, d omega is d alpha, omega minus tau is again alpha, right? I'll again write this equation in terms of alpha now. So this is what I have, and I have this 1 over 2 pi square, right? That I had clubbed 1 over 2 pi to 1 over 2 pi's. I'll use them separately, right? Because I'm trying to make this into a form that would be in the desired form. So let me write this 1 over 2 pi minus infinity to infinity, right? This is again x of tau. The first integral is essentially unchanged, e to the power j tau t d tau, right? What about the second integral? The limits don't change, right? The limits are still minus infinity to plus infinity. So sorry, I'll use them minus infinity to plus infinity. Y of omega minus tau, that is y of alpha, as discussed before. E to the power j omega minus tau t, that is e to the power j alpha t, right? And d omega is d alpha, right? So now, okay, so I had 1 over 2 pi's. I used one here. I missed out the other one. Let the other one be here, right? Now help me out. What is this by definition? And what is this by definition?
Fourier transform.
Yeah, is it Fourier transform or inverse? This by definition is inverse Fourier transform, right?
Okay, sir.
This is what I'm trying to say. Wait, I can in fact show you this equation, right? Notice this 2 pi and positive e to the power j t, right? Let's go back to our equation, right? So I'm using that. See, tau is essentially variable of integration. I could use another step and say, now I'm changing the variable of integration to omega and then write x of omega e to the power j omega t d omega. That essentially is the same thing, right? So I'm skipping that step. I'm directly writing that this is x of t. Similarly, what can you say about this thing?
Y of t.
Yeah, this is y of t. So what did I prove? I started with this inverse Fourier transform of this particular quantity, right? And I proved that the inverse Fourier transform of this property is this. So that essentially means that the Fourier transform of x of t into y of t is the quantity inside this, right? And that was what I was supposed to prove in the question, right? What is the Fourier transform of this? You can either memorize this result, or if you need, this is the proof how it comes about. Then we'll move on to the next question. Should I repeat anything?
No, sir. Please
Okay.
go.
So the next question is the Fourier transform of t cube x of t. I'll wait for a minute or so and then start doing it myself. Meanwhile, you can try this.
Sir, I am not able to solve this question, sir. I have not done all the lectures,
Okay.
sir. I was sick, sir.
Okay. Yeah, I remember you did not even join the last week's
Sir,
interactive
last week there
session.
was GATE exam, sir.
Okay, there was a gate exam last week. Okay, I was not
Yes, sir.
aware of that. Okay, so did you give the exam?
Yes, sir.
How was it?
Sir, okay, okay. Not
Okay,
good, not bad.
okay, fine, average. So, so essentially what we are doing is we are going over through some properties of Fourier transform, right? And today's session was essentially using these properties in the questions,
Okay,
right?
sir.
So you can in fact watch the previous session as well. In that, the Fourier transform was introduced, and I used some properties in the previous session, but today's session is all about using the properties of Fourier transform. Okay, so
Okay,
I'll
sir.
still uh, cover whatever basics I can in this video. And meanwhile, if you have any doubt, you can drop me an email and we can continue from there on, right? Meanwhile, Neeraj, you had that doubt, right, regarding that question. Do you remember?
Yes, sir. Shifting and scaling related.
Yeah, I actually answered that in the recorded video itself. If you would
Okay,
notice,
sir.
I had, yeah, just check. I mean, I did text and that would take care, right? Just let me know if you are satisfied. So
Okay,
this
sir.
is the question, the Fourier transform of t cube x of t. Okay, so this essentially is multiplying by t in the time domain, right? So let's see. Can you see why I should use this property? There is a t multiplication factor of a t in time domain. That was asked in the question, right?
Yes, sir.
So what this property states is that you can go into the proof later. I'll just cover the statement part of this property. Given this x of t and its Fourier transform x of omega, right? The following holds good. If we'll take a derivative of x of omega in the frequency domain, in the time domain, minus jt gets multiplied. Okay, so we'll make use of this property to solve the question, right? And what was the question though? The question was, you have this signal. What should be the Fourier transform of this particular signal? So I notice in the generalized case, I mean, n can take any integral value. So if this n is 3, this is minus jt cube x of t, right? d3 by d omega x of omega, right? That's how I'll proceed. Let me explain what I meant in detail now. Okay, so we have the following signal. X of t, sorry. Yeah, I mean, let me first write the property though. And right, that is essentially the statement of this property. This property is known as the, I mean, differentiation in the frequency domain, whatever you call it. So this was question 5. Okay, so, and in our case, this x of t is t cube x of t. So we need to compute what is the Fourier transform of this particular. Let me write it. Right, this is the question. So I'll use this one. Right, first, uh, x of t would have this uh, Fourier transform x of omega, right? And result is in terms of omega. Other version of this question could have been, in case of x of t, I would have given you a function in time domain whose Fourier transform you would already know, right? And then in the options, instead of this x of omega, it would have been the Fourier transform of this x of t, right? So
Okay.
essentially this question is general, right? We are writing x of t. This could be any time domain signal. So let's use this property. Minus jt. I'll use 3 instead of n because I have a t cube, right? X of t and a third order derivative with respect to frequency x of omega. Right. So this would be, I mean, I can write this minus j, I can write as, let me first write it separately. This is minus j cube t cube x of t having a Fourier transform d3 by d omega 3 x of omega. What is this minus j? Can I write that as 1 over j?
Yes, sir.
Right,
Yes,
I can write that. So this is 1 over j cube then, right?
yes,
1 over j cube t cube x of t d3 by d omega cube x of omega, right? And then what I can do is I can take this 1 over j cube here. I mean, if I multiply both sides by j cube, this would be 1 and I'll have j cube here, right?
yes,
Let
sir.
me
Yes.
do that. Okay, so which option is correct?
So second one.
Yeah, but notice there is this j inside this differential, right? Differential of j omega, that is j times d of omega. Wait, it stopped. See, differential of j omega, that is j times differential of omega, right? And then this j, this would be j square, right? So the correct answer is which option?
Last one.
Last one, yeah. Option D was correct. Option 5, I mean question 5 is done. So now we have the Fourier transform of x of minus t. Okay, let me give you a hint on this one and probably then you can solve it, Neeraj. Okay, we have this property. Get that given this x of t, x of omega. Then if we take the convolution, I'm sorry, convolution, the conjugation, right? If we conjugate the signal in time domain, in the frequency domain, we need to conjugate the signal along with this time reversal. Okay,
Okay.
so given that you know this, what should be the answer of this one? What about this signal? Conjugated signal with a time domain reversal, time reversal. By the way, I can help you out with this time scaling property also. Where is that time scaling property? Suppose that you know this much information, okay? Based on these, can you obtain the Fourier transform of this particular signal?
Yes, sir.
Yeah, so what should be this? See, we know that this particular thing holds good, right? So What about x of minus t? Which property should I use for x of minus t?
Sir, the
This
second
one.
one. Yes, sir.
Yeah, raise minus 1. Now, modulus of minus 1 is plus 1, right?
Yes.
So this factor would be 1. So I'm left with this minus 1. So this would be x of minus omega. Agreed?
Yes, sir.
Now what I'll do is I'll use this property. Okay. Suppose this x of minus t was, say, y of t, and x of minus omega is y of omega. Okay. I'm saying replace this by this and this by this. I can do that.
Yes.
Now use this property on this one. What should be conjugated y of t?
So, conjugate of x minus omega.
Would be
Conjugate of
conjugated of y,
y.
right? Yeah,
Yes.
conjugated of y
Minus omega.
minus omega. Okay. Now, but y of t was x of minus t,
Minus.
right? So this essentially is conjugated minus t,
Yes.
and my this y of omega was x of minus omega. Okay, x of minus omega. So this would be conjugated minus omega. That would be
Okay, sir. Plus omega.
plus omega. In fact, these steps are optional. You can directly come to this conclusion, right? Okay, let
Yes,
me
sir.
put these. I hope it's straightforward, right? Is there
Yes,
any
sir.
doubt?
No, sir.
Okay, so this one was question number 6. Question 6 is done. Now we are left with question number 7. So, okay, so this is the question is that we are given a transfer function and we need to compute what would be the differential equation corresponding to this transfer function, right? Earlier, we saw a question in which the differential equation was given and we had to compute the transfer function. This essentially is a dual of that question. Okay,
Okay,
so
sir.
in that question, we used Fourier transform, and in this question, we would use inverse Fourier transform.
Inverse.
This is how we'll proceed. Firstly, we'll write this transfer function. Okay, so this is the transfer function, and the question is question number 7. So what should be y of, yeah, let me first multiply this. I mean, I use y of omega as notation for this y of j omega, and likewise for x of j omega, right? So I'll write this in terms of my notation first. 3j omega plus 2, 8 minus 2 omega square plus j omega. Again, this and this are same, right? Just a matter of notation. So then let me multiply this y of omega by 8 minus 2 omega square plus j omega, and this x of omega by this 3j omega plus 2. Okay, so this then can be written as 8 y of omega minus 2 omega square y of omega plus j omega y of omega, that is equal to 3 j omega x of omega plus 2 times x of omega. Okay,
Yes.
so taking inverse Fourier transform of this one is straightforward. This one is straightforward. But what about this, and this? We are essentially multiplying by j omega in the frequency domain. And in fact, I'm doing the same for this as well. I can write this minus 2 omega square as plus 2
Mm,
j omega square, right?
yes. Yes, sir.
So, so essentially throughout I'm multiplying by j omega or j omega square and or powers of j omega in the frequency domain. So let's revisit the properties. Which property should we use? Notice looks like we should use this one, right? J omega, if that is multiplied in the frequency domain, in the time domain, we should take derivative of time domain signal x of t. And if we have higher powers of j omega, like j omega square, then this derivative would be second order derivative of time,
Okay,
right?
sir.
So that is what we would use. This would be 8 times. I'm using inverse Fourier transform throughout. This would be 8 y of t. This, I guess I can write this in this step itself, that this is plus 2 j omega square. Okay, so that you don't get confused. So what should I write? 2 times?
So 2 times d and
Yeah, d, but n is
d
2, right?
squared
So that's why second order derivative of y
yt.
of t. Yeah,
Yes,
y
sir.
of t plus d by dt of y of t. That is 3 d by dt of x of t plus 2 times x of t, right? Then what we can do is we can go over through the options and see which one is the correct one. Which one is the correct one? Plus 8 y of t. Okay, so I guess only there is a plus 2 with second order derivative. So I'm left with these.
Yes, sir. The last
Uh,
one.
Yeah,
There are
looks like
positions on left hand
option
and
D.
right hand.
Yeah, so option D is correct. So with that, I'll move on to the next question, which is uh, finding this Fourier transform of the signal x of t. Okay, this x of t is a signal whose Fourier transform we have been provided, and we need to compute the time period of that x of t signal, right? So notice we need to do two things. The first one is we need to compute the inverse Fourier transform of this one, and then once we get that x of t, we need to compute the time period, right? We
Okay.
are well aware how we can compute the time period, right? So let's see how we can do this one. This one is question 8. Okay, so question 8 is we have been given x of omega, that is del of omega plus del omega minus pi plus delta omega minus 5, right? Now, what about this x of t? What is the inverse Fourier transform of del of omega? Okay, so let me help you out. Fourier transform of 1. What is Fourier transform of 1? That is 2 pi del of omega. Okay, so what is inverse Fourier transform of del of omega?
1 by 2 pi.
Yeah, 1 by 2 pi plus. Okay, this is essentially the same signal, but where frequency is shifted by pi units, right? Let's see
Yes.
what happens when frequency domain is shifted in the frequency. That should be this one, right? In our case, this omega naught is pi. Okay, so
Okay,
the
sir.
time domain signal is multiplied by e to the power j omega naught t. Since in our case omega naught is pi, so this would be e to the power j pi t getting multiplied to the x of t, right?
Yes, sir.
Okay, so this is x of t multiplied by e to the power j pi t. Similarly, what should be the inverse Fourier transform of this one?
Sir, e to the power j5t by 2 pi.
Yeah, 1 by 2 pi multiplied by e to the power j 5t. Okay, now this was part one of the question, right? I guess I should even write the property which I had used. Otherwise, it would see the property because given x of t, x of omega, then x of t e to the power j omega naught t, x of omega minus omega naught. Okay. Okay, so there were two parts in the question, right? The final part was to compute this time period of this resulting signal x of t. So now, what about this? What should be the time period? Okay, why is it not working? Okay, what should be the time period of? Okay, what about this one? This is mere constant, right?
Yes,
Will
it
not
is
change
periodic.
that 1 by 2 pi will not change periodic because see, suppose I have a periodic signal sine of omega t.
Yes.
Okay, if I do a plus, what would happen? See, this was the
Yes, this
original
will
signal.
shift in the
Yeah,
y direction.
but period won't change, right?
Yes, the period will remain same.
Period will remain same. So the period will be determined by this and this.
Yes.
Okay, so let the periods be this one be t1 and this one be t2.
Yes, sir.
Okay, so this one is t1. What is this t1 equal to?
2.
T1 is 2, right? Because it's 2 pi divided by pi. That is
Yes,
2.
sir.
What about this one? What should be
Sir, 2
T2?
pi by 5.
It should be 2 pi by 5. Okay. Now, remember we did a similar question. Now, essentially the question is that we need to compute the period of sum of two periodic signals,
Yes,
right?
sir. Yes.
We saw how to solve such kind of problems, right? So,
LCM.
yeah, see, we have T1 equal to 2 and the other one is T2 equal to 2 pi by 5. So are you saying this periodic? Why?
Sir, the ratio of the two time periods is an irrational number.
Yeah.
Yeah, but it is
because
a periodic.
exactly, because no matter, suppose I take multiples of this one, right? I take any multiple, say suppose k1 times this time period t1. I won't be able to find k2 times t2, right? Such that this equality will hold if k1 and k2 are integers. That is essentially what you said. This t1 by t2 or t2 by t1 is not rational. It's irrational in this case. So x of t is periodic. Sorry, I mean a periodic. Option C should be correct, right? So with that, we'll start with our next question, which is question number 9, which is to use the properties of Fourier transform to show by induction that Fourier transform of this particular signal is this one. N is not working. Just a second. Yeah. Must have solved questions on this induction based problems, right? Aware of them?
Sir, I don't remember that clearly, sir.
Okay, see, what we do is we see if the result makes sense for n equal to 1, right? And for any other value of n if needed, then we assume that it's true for n equal to k, right? We assume this, that this is true for n equal to k. And then using all these, we prove that this result is true for n equal to k plus 1. Then we say that by the principle of mathematical induction, the result is true for any n, any n.
Okay, sir.
Okay, that's
Yes, sir.
what this principle is. So, I mean, this exercise would essentially revise some properties. That's why I kept this as a question. Okay, so given signal is e to the power n minus 1 factorial e to the power minus 80. Right, this is what we essentially need to prove. So as I said, we'll start with uh, n equal to 1. Okay, what happens when n is equals to 1? This is t to the power 1 minus 1, that is t to the power 0. 1 minus 1 is 0 factorial, that is 1. So this is e to the power minus 80 u of t. Okay,
Yes, sir.
that is 1 by a plus j omega.
J.
And that is actually a standard result. E to the power minus 80 u of t. The Fourier transform of this signal is 1 by a plus j omega. If you do not know this, I mean, if you are not aware of this, you can go through the week's lectures, Neeraj, and we'll come to this conclusion. Okay.
Okay, sir.
So this is something that holds good. So what we'll do is, let me see what happens when n is equals to 2. When n is equals to 2, I would have t e to the power minus 80 u of t, right? Because 2 minus 1 is 1 factorial.
Yes, sir.
So this is 1. 2 minus 1 is 1. So that's why this t factor. So this t x of t and x of t is this one. The Fourier transform of that, the Fourier transform of that is, okay, this should be j d by d omega 1 by a plus j omega. Why? Differentiation in frequency domain. Just we have this, right? So I have used that property. See, it was this way around, right? It was minus jt times this particular factor times d by, I guess I should skip a step. Okay, I'll show in between steps with this gray color. Minus jt e to the power minus 80 u of t d by d omega of x of omega, but x of omega is 1 by a plus j omega. Okay, and then what I'm doing is this minus j. Minus j is 1 by j, and that 1 by j, what will happen to that 1 by j when I take that here? That would be j, right? Okay, so if this is x of omega, then what is d by d omega of 1 plus j omega? A plus j omega square, the denominator square, denominator times the differentiation of numerator, but the numerator is 1, so its differentiation is 0. So I'll have a minus sign. Now numerator, this 1 times the differentiation of denominator, and differentiation of denominator is j, because I'm differentiating with respect to omega. I'll have j. Okay, now This is what I got as a derivative. Wait, did I miss something? It's fine. Okay, and d by d omega is this one. So j square is minus 1 and minus is plus. So this would be 1 by a plus j omega square, right? In agreement with this one. So okay, it does make sense for n equal to 2. Now let's consider the case when this n is k, and we'll assume that it is true for n equal to k. We'll assume it is true for this n equals to k. Okay, so what is x of t when n is equals to k? X of t would be simply replacing n by k. T to the power k minus 1 whole divided by k minus 1 factorial e to the power minus 80 u of t. Okay, and x of omega would be 1 by a plus j omega raised to the power k, right? Replacing this n by k again. Now what we'll do is, this is something that we'll assume. Okay, now we'll consider the case when this n is k plus 1, and we'll prove that it is true for n equal to k plus 1. We consider the case when n is equals to k plus 1. So this x of t would be t to the power k by k factorial a to the power minus 80 u of t. I've replaced this n by k plus 1 in this. Now I need to prove this one. Okay, I have this one. I need to prove this for n equal to k plus 1. So given this x of t, what should be x of omega? X of omega should be, see, I know this result. This is something that I know because I'm assuming this to be true, and I can use that in this. So let me do that. So this is essentially d by d omega of 1 by a plus j omega. See, I hope you understand what I'm trying to do. I've written this in this form. Okay, then I know that for this, I know the result already. So what should be the result when it's multiplied by t, like we did for this case, right? When it's multiplied by t, there is a factor j, right? This is nothing but a corollary of this. So this would be, this j is because of that t, and this k would remain as such. Okay, and yeah, why I've taken derivative of this particular thing? Because the Fourier transform of this is this. So when I multiply this by t, the Fourier transform of the resulting signal would be the derivative of the Fourier transform of this one. Okay, now what is then x of omega? X of omega would be j by k times this. I can write this as d by d omega of a plus j omega raised power n. I mean the form. So what I can do is I can write this one, a plus j omega raised power minus k, and then I'll use, I mean this is essentially differentiation with respect to omega. So what I'll do is I'll write x of omega as j by k. This minus k would be here, and this would be a plus j omega. What should be the exponent? The exponent would be
Sir, minus k plus 1.
minus k minus 1, right? The differentiation of x raised power n is n x raised
X to
power
power
n
n
minus
minus
1.
1.
Yeah, that's why I've written this minus 1. Okay, so this part is clear. Okay, so I'll still have something, right? What the differentiation of this? Am I missing something? I should take differentiation of this as well, right? With respect to omega.
Yes, sir.
Yeah, what would be that? With
Sir, it will
respect to
be
omega? With
plus
respect to
j only.
omega? Yeah, plus j only. Now, this j and j is j square. J square is minus 1. That minus 1 and this would go. This k would go. So I hope you understand that we'll have
Yes, yes, sir.
x of omega as, essentially this everything goes away. A plus j omega. I'll write this. Okay. Then I can write x of omega as 1 by a plus j omega. This is exponent k plus 1. Okay. So that
Okay, sir.
is what we needed to prove. So therefore, what we can conclude is, therefore, we conclude it's true for all n. Okay, that's how you use principle of mathematical induction. So that was my last one. Okay, yeah, regarding your that question, Neeraj, you can watch that video, and if needed, we can discuss in the next session, or you can let me know through email if you have any doubt. Okay, do watch that one.
Okay, sir.
Any other question from today's session?
No, sir.
As I'm done with mine part. So I guess we should wrap it up.
Okay, sir.
Yeah, that's all from my side. Thank you.
Okay, sir. Thank you, sir.
Yeah, bye.